Good morning, good afternoon, and good evening, everyone. Thank you for joining us for this second series of Community Lightning Talks on the theme, this time, of building resilience. So the objective is for us to think and discuss about how GIS can help not only respond to disasters, as we saw yesterday, but also how we can better prevent them and prepare ourselves better to mitigate their impact. Ultimately, we're talking about reducing the risk that different sorts of hazards pose to lives and livelihoods. So the first step of any risk reduction effort is to understand that risk. Understand the probability of a hazard of a particular severity occurring, understand the exposure of people and assets to these potential events, understand their vulnerability or how badly they will be impacted, but also understand their adaptive capacity to known hazards, as well as their coping capacity if a hazard hits. All these factors are what constitute risk, and it's crucial to understand that risk if we're to do anything about it. So GIS are ideally suited not only to understand these factors, but then also to provide insights and options on anticipatory actions that can be undertaken to either reduce the likelihood of a hazard occurring, reduce exposure and vulnerability to them if we can't do anything about the hazard itself, or increase adaptive and coping capacity of communities. So together, these insights and actions help reduce risk to lives and livelihoods. You could also say that they increase our resilience. So you'll now hear a series of presentations by a number of your peers on how they and their organizations have applied GIS to build resilience for their communities and reduce risks. These will run for the next 25 minutes or so, and you will then have the chance to put your questions to the speakers in a live Q&A session that will run to the top of the hour. So with no further ado, I'll switch over to our first presentation and hope to see you for a live discussion with our speakers in a little bit. Enjoy.
Greetings from Resilience Mappers Uganda, and thank you for attending this session, developing a web map repository of Kampala's informal settlements. I am Solomon Kisa, the Community Manager of Resilience Mappers Uganda. I'm pleased to be presenting at this year's GIS for a Sustainable World conference. Resilience Mappers is an online mapping community formed in March 2020 by final year land surveying and geomatics students at Makerere University in Uganda after the closure of schools and universities due to the COVID-19 pandemic to quickly respond to providing map data in areas where government and aid agencies expect to or have intervention programs in Uganda. The community has grown to include 44 volunteers who assist in mapping and validation. The growth of informal settlements, slums, and poor residential neighborhoods due to a rise in urban population in cities has become a global issue, and Kampala is no exception. The characteristics of these settlements, such as high density and unplanned, crowded houses, together with a lack of infrastructure, have led to acute problems including poor drainage, sanitation, and solid waste management. In April 2020, the Uganda government launched a relief program to distribute food to the vulnerable poor living in the urban settlements of central Uganda. The recipients were workers who worked hand to mouth and were directly affected by the drastic measures to contain COVID-19 infections. Despite the delayed food and relief distribution due to a lack of complete spatial data, there was a risk of underestimating the virus's magnitude when established in these communities, fueling unequal allocation of healthcare resources. With support from humanitarian OpenStreetMap team, we were able to train 7 mapping communities on how to contribute to OpenStreetMap and assist in mapping these informal settlements. We employed several open source geospatial tools, ranging from remote mapping to validation of data, to equip as many volunteers as possible with the necessary skills to map these settlements. These tools were Java OpenStreetMap Editor, ID Editor, and MapLarry. With the COVID-19 restrictions, the informal settlements could only be mapped remotely. Data obtained from remote mapping included outlines of buildings, land use types, and roads covering over 8 square kilometers of the settlements. We were able to map the buildings, land use, and roads in 15 out of the 56 informal settlements in Kampala using Esri world imagery and mapillary. Since there was no single inventory that could be accessed by members in the community and aid agencies in the settlements, we created a web map repository for Kampala's informal settlements using ArcGIS Online Africa Geoportal account. It offered several benefits over paper maps, such as being quick and efficient to monitor, easy to update, allowing quick retrieval and queries, and offering faster integration of complex, multiple spatial and non-spatial datasets. Statistics such as population in these informal settlements, the number of health centers, schools, police stations, the number of buildings, and the number of waste dumping sites could be visualized on a dashboard, which can also be accessed by community members, aid agencies, government agencies, and donors. The web maps created were shared with stakeholders including urban authorities and community-based organizations to assist in their intervention programs to improve the livelihood of people living in these communities. Having realized that most data and information in the informal settlements are not documented, we are hoping to work closely with urban authorities and community-based organizations to devise means of collecting and updating the information in these settlements. With support from humanitarian OpenStreetMap team and Esri, we will be able to update schools, waste dump sites, and health facilities data in these communities. Besides having a successful outcome, we learned many lessons from challenges. Continual discussions and meeting with stakeholders, especially the data users, is vital. It helped us drive our activities based on the needs of the data users. It also provided ideas and schemes that could make our data more beneficial to other related authorities in case they may need the data at one point. Thank you for your attention and for attending this session.
Hello, my name is Diego Gonzalez, the Geospatial Data Lead and Unite Maps Product Manager at the United Nations Global Service Center based in Brindisi, Italy, from where we deliver location-based services and products to several UN entities like peacekeeping missions and political missions in the field, from where we support their colleagues in carrying out their daily activities related to security, peace building, logistics in the host countries.
Today I'm going to talk to you about the Unite Maps program, an initiative that aims to provide a wide range of mapping products built on top of Esri technology, like for example base maps at the street level or satellite imagery level, operational data carried out by the UN, 3D applications, and search and direction functionality based on geocoder and routing services. But specifically, I'm going to talk to you about a self-serving desktop application called Maps on Demand that empowers non-GIS UN staff to dynamically create topographic, urban, or site maps or focus maps of specific areas of interest at various scales. This application is built on top of the product on demand, an Esri JavaScript application built on Esri production mapping for server, and it is fed with the latest available data from United Nations authoritative repositories, field missions datasets, and other publicly available sources, especially OpenStreetMap. So let's go for the demo. We start off from the Unite GeoPortal, our own geospatial content management system within the UN, and we search for the Maps on Demand application. We find the portal item, we open it, and we sign in. The first thing that we will see is a splash screen with a disclaimer that we have to accept. And in this simple user interface, we have several mapping products that we can create: topographic maps, urban maps, or site maps. In this case, I am searching for Bangui, the capital in Central African Republic, because I want to create a city map. I select the page size, the scale, and the paper orientation. I click on the map to select the center of my map frame, which I could even change. I click on the export queue of this specific mapping product. I add the map title and the email address for further notification. I can select the points of interest. And I click on the export product tool. If I want to create, for example, a map of a UN camp in Abyei, a town between South Sudan and Sudan, I go and click on the sitemap. I can change my base map for further clarity. In this case, I want to change the scale to 1:5,000, and I click on the map frame on that UN camp that is visible on the satellite imagery. I click in the export queue on that product. I add the map title, the email address, and I click the button export products, and I let it run. Now I am interested in creating a topographic map. The scale is 1:50,000. We can see here the map index with all the different map sheets available. I am particularly interested in a map sheet covering Butembo in northeast Congo. I add the email address for notification, and I export the products. I let them run for a few minutes, and I have them ready. I received my notification on the email inbox, and I open it. As you can see, this is the topographic map with all the contour lines and all the terrain features. The data is coming from OpenStreetMap mainly. I also click in the application on the link to download the sitemap with the satellite image as a background and operational data. And in this case is the Bangui city map with all the information coming from the various repositories. The first one that we have is the data sources are coming from different repositories. We put them together within the GIS workspace. We work internally and also externally with the UN mappers community that we have established to improve the data on OpenStreetMap to feed the Maps on Demand application. We are going into expanding to many different countries. At the moment, we have these 6 that you can see on the screen. And please collaborate with us and the UN mappers. We would be extremely grateful if we can work together for a sustainable peace and development. Thank you.
I am Rahim Dobaria, Associate with Aga Khan Agency for Habitat, an agency of Aga Khan Development Network. Aga Khan Agency for Habitat, AKA, has been working on disaster risk reduction program for over 2 decades, and I am going to present the case Hazard, Vulnerability and the Risk Assessment HVRA approach being used in AKA. GIS technology has become the backbone for AKA, allowing analyzing risk to properties and human lives. GIS is an integral part of AKA and extensively used for DRR in all the stages of disaster management, starting from the preparedness, response and recovery. The HVRA framework developed around GIS technology greatly helped to assess the risk of more than 2,500 settlements in the AKA area of operation in Afghanistan, India, Pakistan, Syria and Tajikistan. HVRA is the systematic approach to identify hazards and its risks that are most likely to have an impact on the community. It is a tool to evaluate the potential risk on the people, property, infrastructure and environment. HVRA framework developed around GIS technology is fundamental and first step of AKA work for DRR intervention. GIS is the foundation of AKA works, and across academic agency we have internalized risk screening process with the scientific approach. The HVRA standard methodology developed around the GIS determine extent to which community are exposed to hazard and degree of vulnerability. Risk is defined based on 2 main pillars or indicator: hazard exposure and vulnerability. Each indicator has certain sub-indicator, like vulnerability indicator is defined based on three sub-indicators: susceptibility, coping capacity, and adaptive capacity. Each sub-indicator are defined based on several parameters. The methodology exposure index allows to determine who is exposed and who is most, while vulnerability index allows to determine who is vulnerable and who is most. HVRA process consists of 4 stages as summarized on the right side. Start with an offsite desktop assessment, followed by on-site field assessment, then validation and generate analysis in form of maps and statistics. Dissemination of the result is the final stage in which generated analysis and finding communicate to the relevant stakeholder in a form of document through a presentation and discussion. The result of the HVRA incorporated in the village disaster management plan. This is the point where we identify and develop implementation plan for DRR intervention. We develop all the product and tool using ArcGIS tool. Here we can see one example of ArcGIS Zero database, which provides the native data structure to store, query, and manage both spatial and non-spatial data. On the left side, we can see the hierarchical structure of the HVRA dataset, while on the right side, screenshot of the HVRA Zero database in which all the HVRA data being stored. GIS technology has been effectively used in ACA DRR intervention and help decision maker and other concerned stakeholders to design an accurate operational picture of the critical scenario before, during, and after disaster. These are the list of the example. However, I will talk few of them in next couple of slides. Here is the risk map of one of the settlements of Afghanistan. It is multi-hazard focus, where we can see the village is exposed to avalanche and flood. Many houses and buildings are exposed to avalanche and flood. Such a map are generated for all the settlement where ACA work. This map helps for risk-sensitive planning, prioritize intervention, and develop hazard-specific program. This is another example from Tajikistan of Korok city. It has over 25,000 population. You can see the city is exposed to multiple hazards like debris flood, landslide, rockfall, flood, avalanche. This is the example of avalanche monitoring and forecasting system. We have identified over 600 settlements in mountain area which is prone to avalanche. We have established a modest kind of localized weather monitoring post that is manually operated by local community in the 88 high-risk locations. It collects daily weather parameters like the temperature, snowfall, and also local conditions like snow depth on the ground. The data further analyzed by an avalanche expert and issue a weekly bulletin, which help us to alert the communities and mobilize resources if necessary. This is an example of life-saving capability of science and technology. Whenever cyclone form over the Indian Ocean, many international weather monitoring agencies issue the warning in form of bulletin. This is one of the case of cyclone Leher 2013, where we mapped the forecast track using bulletin and overlaid HVRA data. It shows the time when cyclone landfall and passes over the particular area. This helped timely mobilize volunteers, stockpile, and other resources on the ground. Emergency communication and early warning system is also installed in high risk and remote area. Thank you very much.
My name is Oran No, and I work for the United Nations Institute for Training and Research, UNITAR. At the UN Operational Satellite Applications Program, I'm currently managing the flagship project called Common Sensing that aims to help improve climate resilience in small island states in the Pacific. At today's lightning talk, I would like to provide the overview of the project and showcase how the GIS and remote sensing tools are being used to support the partner governments in making evidence-based decisions for strategic planning and enhanced access to climate finance to achieve a sustainable future. Common Sensing rolled out in 2018 with the overall objective to build resilience towards climate change and contribute to the sustainable development in 3 selected Pacific states, namely Fiji, Vanuatu, and the Solomon Islands. The project is funded by the UK Space Agency through the International Partnership Programme, and it brought together 8 organizations with world-leading expertise in satellite remote sensing, sustainable development, business analysis, data modeling, and climate financing. Unitar UNISAT, as a lead organization, deployed 3 in-country experts who are hosted within the focal ministries and have frequent interactions with key stakeholders on a daily basis. Project thematic areas consist of 4 components, as can be seen in the slide: climate information, food security, disaster risk reduction, and climate finance. During this scoping phase, we learned that the common issue across these areas is the lack of baseline data at the national and sub-regional levels, and access to it. Thus, Common Sensing proposed the holistic solution comprising of the technical platform and capacity development activities. Common Sensing Geospatial Platform, based on the Esri system, has been developed and tested in Fiji. This infographic represents the overall functionalities and the type of data that are presented on the platform. The portal provides access to both current and historical information. Most data cubes contain all the satellite imagery for an area back to the 1980s, and by looking at this, it is possible to see changes over time in terms of coastal erosion or deposition, deforestation, urbanization, and landslide activities, among others. On the platform, users can access to future climate scenarios and overlay them with other layers to better understand impacts. Lastly, it also helps to understand existing and future risks in specific locations regarding exposure to natural hazards and communities' vulnerability level. We believe the evidences and data provided by Common Sensing will help also partner countries' applications for global climate funds with a higher degree of success than present. And it will enable these countries to obtain the necessary funding to protect critical infrastructure, build resilience into their economy, and combat the growing effect of climate change. Common Sensing also has delivered various training for government officials and relevant national and regional stakeholders to ensure they have adequate capacity to fully utilize the provided technical platform and tools for their decision-making. These events were tailored to users' needs and country-specific contexts. The overall goal was to strengthen institutional capacity in country, to translate the data into actionable intelligence for policymaking and actions on the ground. How has the Esri technology helped the Common Sensing project to achieve its goals? This slide shows a few snapshots of tools provided by the project consortium for 3 partner countries. The first 2 on the left side are the Common Sensing main portal for Fiji and decision support system that has tailored pages for each partner country. Its functionalities and the type of data were explained in the earlier slide. In the middle and on the right, they present a few highlights of technical backstopping services were provided for the National Disaster Management Offices in Fiji, Vanuatu, and the Solomon Islands. The Flood Susceptibility Web Map using simple digital elevation models was generated, and it recently proved its high degree of accuracy when Cyclone Nana arrived in Fiji this year. This live web map is now being part of the NDMO's decision-making chain. Also in the Solomon Islands, the monitoring dashboard for the control of COVID-19 quarantine stations is actively supporting the national risk management in the health sector. By zooming and clicking the interactive map, you can easily get regional breakdown data. The bed capacity and its occupancy together with gender breakdown, you can find them all on the board. Last year, Tropical Cyclone Harold caused devastating damages in the Pacific region. For Vanuatu, We've brought an interactive dashboard and 3D web map to help tackle with the emergency responses. The dashboard had not only satellite-based information, but also other vital information such as the total number of casualties and the location of emergency operation centers at national and provincial levels. Statistics changes with map extent. NDMO highly appreciated the interactive dashboard as it helped real-time monitoring for deployment of intervention teams and distribution of relief goods. If you're interested in learning more about the highlights, please visit the link at the bottom. We hope common sensing solutions can be replicated in other Pacific countries or small island states in different regions. They are also vulnerable to climate change. Space-based solutions are most cost-effective compared with other similar solutions using unmanned aerial vehicle and aircraft imagery, well, thanks to its better precision and accuracy of the mapped areas. Please feel free to reach out to us if you see opportunities for collaboration or sharing lessons learned. Thank you for listening to my presentation.
The United Nations World Food Programme, using Esri tools to transform complex satellite data into actionable information. My name is Sarah Muir, presenting today on the Asset Impact Monitoring from Space interactive platform. Assisting almost 100 million people around 88 countries each year, the World Food Programme is a leading humanitarian organization delivering food assistance in emergencies. The Food Assistance for Assets program is a WFP program that helps to meet the immediate food needs of food insecure people, while also building assets to help strengthen their livelihoods, to reduce the risks from natural disasters and make them and their communities more resilient to shocks. The AIM service identifies and monitors landscape changes induced by WFP FFA projects using Earth observation data. Assets may include soil and water conservation measures, feeder roads, and irrigation systems. The AIM service began as a pilot project back in 2017 with the support of the Innovation Accelerator. Since then, AIMS has supported asset monitoring across all regional bureaus in 18 countries. Last year alone, we monitored over 1,200 assets. Needless to say, what began as a small pilot project has evolved significantly. In order to sustain the service and support the growing number of users, AIMS has migrated to a web-based platform using Esri solutions. Before going into the details of the platform, I'd like to take a moment to highlight the key service offerings. The first component is asset detection, and the second, landscape impact assessment, where landscape impact assessment uses open source time series data, satellite data, to measure the impact that the community's productive assets has on vegetation condition. The aim is to build evidence of the positive impact that the FFA program has on the landscape. Asset detection, on the other hand, is using commercial high-resolution satellite imagery to visually identify the asset. Where the first version of the platform has focused on asset detection, the next version will incorporate landscape impact assessment. The objective of the platform is to improve the communication of information with colleagues at the country office level, making AIMS analytical results easily accessible and enabling colleagues to quickly grab project summary information as required. We also wanted to build in the ability to interact dynamically with the satellite imagery at the project site and to produce asset detection maps on demand. There are 4 parts to the platform. The global, regional, and country office pages are all externally accessible and serve as advocacy tools for the program. The interactive country dashboard sits on the internal WFP network as advanced security measures are needed to protect the data. So the goal was to create one location to house all of the AIMS data. This includes the satellite imagery, the details on the asset, such as the start date and the end date, the project size, and also the AIMS analyst observations, visible, not visible, and reports and advocacy material. The internal interactive country dashboard provides summary information about FFA projects, total projects monitored by AIMS, the different types of activities, and of course, the analytical observations from the AIMS service. The central map shows the geographical distribution of the assets. This can be further narrowed down using the filter widget by the user. The dashboard makes use of the image slider widget that allows the user to visualize all of the imagery available at the specific site. Additionally, the image comparison tool facilitates a direct comparison between two images, and this is needed to compare before and after the project implementation. Users are also able to add annotations and estimate the project area using the draw widget, and this can be exported to a map using the print service. This brings me to the end of the AIMS platform presentation. Thank you for listening.